Hi year 8, this is your next revision video and it's on the topic of 10.3, which is on page 92 in your textbook, Temperature and Catalysts. Now, some chemical reactions happen almost instantly, like explosions, and others like rusting or acid rain corrosion take much longer. So there are several factors that can affect how fast or slow a chemical reaction can take place. And our knowledge of particle theory of matter, sometimes referred to as kinetic theory, can give us the explanation for these factors. So let's just have a quick look. First of all, we're going to define what a reaction rate is. So a little feature, a little sneaky peek into the video by a little Melon there. So hi Melon, there you are, you're actually there, creeping in the background. Reactions can take varying amounts of time from start to finish. Okay, so when we're monitoring a chemical reaction, what we like to do is we'd like to monitor either the amount of product that is made and try and figure out how much is made over time, or how much reactant has actually been lost. This is a gas reaction which will, this is a solid reaction with a solution, perhaps it's an acid, and a gas is being lost over here. So the gas can actually escape through this apparatus over here, because this is a cotton wool to stop the spray and stop the escape of liquid, but the gas can escape through the cotton wool, and in this conical flask, a reaction mixture, you'll actually find that you have a decrease in mass because gases have mass. A lot of people don't realize that, but it's true. It is true. If you blew up a balloon, it would actually weigh more than the empty balloon. If you don't believe me, try it with a set of kitchen scales that are very sensitive. So these are two ways of monitoring reaction rates. There are several ways of monitoring reactions rate, but these are just two methods. And yeah, so reactions can take different amounts of time from start to finish. And what we want to do as chemists is we want to be able to show the amount of chemical used, which would be here, or the amount of chemical produced, which is here, in a set time period. If there's a lot of it that's used or a lot of it that's made in a fixed amount of time, like in a minute, or an hour, or a second, or a day, then we actually have a very fast reaction. Okay, what we mean to say is we have a very high reaction rate. Notice what I used, the different words that I used. You talk about reaction rates as being high or low because reaction rate is actually a number. Okay, so to explain reaction rates, here's a little reference to particles. So sometimes you have an unsuccessful collision taking place, and sometimes you have a successful collision taking place. So think about your particles, think about how gases are, think about how particles exist in liquids. They're moving all the time and they bump into each other frequently. However, they don't always react. So for particles to react, they must collide with enough energy to break the existing bonds in the atoms or molecules. And we looked at bond breaking and bond making in our previous video in 10.2. Once you have these bonds broken, atoms can then rearrange to make the product. So just quick reference to my last video, bond breaking requires energy to be put in. Bond making releases energy. And sometimes you find that the bond making is greater than the bond breaking. That would be for an exothermic reaction. And if that happens, you actually find that the energy given off by bond making can then help increase the reaction rate even further for reactions that have not taken place, because they're obviously warming their surroundings, including reactant particles that have not reacted at all. So you can actually have a runaway reaction rate, and that is more often than not what you find with things like fireworks and explosions. So there are many factors that do affect the behavior of particles, and all of these will actually have an overall impact on the rate of reaction. But it's very important for you to realize that it's not just the case where they just bump into each other and they automatically react. They actually need the energy, they need to have the store of energy in order to cause a successful collision, to overcome the barriers that exist between particles in order to react successfully, which is the reason why temperature is such an important factor when we're talking about chemical reactions. When we heat chemicals, we are actually trying to speed things up. And as particles gain that store of kinetic energy, what happens is they move faster. If they move faster, they have a better chance, a higher probability of having a successful collision, okay? And remember that collisions are trying to break the existing bonds in the atoms or molecules. So coming back over here, perhaps an unsuccessful collision could just cause a little prang, you know, just a little wobble inside. But if you have a successful collision, that's enough to shatter a bond, okay? So as you have particles gaining kinetic energy, they begin to move more quickly, so they store that kinetic energy in them, and that would actually help with a greater number of collisions because they reach each other much faster, and the particles with the greater speed are more likely to collide, they're more likely to collide, and they're also more likely to have a successful collision. They're more likely to collide because they can reach the other particles faster, and they're more likely to have a successful collision because they've got the energy to overcome the energy barriers required for bond breaking. So when particles have more energy at higher temperatures, they are more likely to have enough energy to react. And as a combined effect, that means that small changes in temperature actually make big differences. So if you actually raise the temperature of a reaction mixture by 10 degrees, that actually doubles the reaction rate. So you get your product in half the time, you use up your reactant in half the time, okay? Fast reactions will cause lots of gas to be produced quickly, and this gives steep curves when you are actually asked to produce line graphs on this. So here's a line graph. We actually put the time that's passed in the chemical reaction and the volume of gas produced on this side. So if the volume of gas is produced very quickly over time, it's like as if the line is dragged towards the left. So here's a reaction that takes place at 75 degrees, but you would expect more volume of gas product as in the same amount of time. You would expect more if the temperature was actually higher. So you can actually see that at 75 degrees for this point, at this point, you would only produce this much. You would expect more, and that's what this is. You'd expect more at a higher temperature. Now, you might think, well, why doesn't this line just get steeper and steeper and steeper and steeper? Well, the reason why is because at the end of the day, you've only got a certain amount of chemical reactant. So if you're actually doing a fair test, you have to use the same amount of reactants. It's just the case that the work by the chemicals will be finished quicker. Okay, a little bit like when you're in class and you find that you're working well, ahead because you're confident with your knowledge, and you actually you actually finish the work much faster than other people do. Okay, so that's the reason why at the end a chemical change in the rate of reaction does not necessarily mean that you're going to actually get more stuff at the end. Okay. Let's put it this way. I'm going to make another analogy. If you bake a cake and your oven is relatively cooler than it should be, it's going to take longer. It's going to take longer to bake the cake. If you have your oven at the right temperature, it's going to take a shorter amount of time to bake that cake, but you're not going to have suddenly two cakes when you open the oven. It just doesn't make sense, okay? Cooking is chemistry at the end of the day. That's what I firmly believe. Okay, so what is really interesting is that this slope of the graph, called the gradient, gives you an idea of the reaction rate. So if you've got a very steep graph, that means you've got a very high reaction rate. Almost made a mistake there. So the steeper the graph, the higher the reaction rate, the faster the reaction. Okay, so we talk about rates as being high, low, but we talk about reactions being fast, slow. Okay. Big difference there. The rate is not the same throughout the reaction. So as the products get used, as the products get formed, the reactants get used up. The reactants are further and further apart from each other because there's less of them there, and less product is made during later stages of your chemical reaction as time goes by. That's why the curve for the individual lines start to flatten out. So when the temperature is reduced, that's one thing. The volume of gas in this graph becomes less, giving a less steep graph. But you also find as time goes by, no matter what the temperature is, as the reactants get used up, you have a flattening of the curve. The curve becomes more flatter because there are less less reactants that are available later on in the chemical reaction. Eventually, you form the same amount. Here it's a gas reaction, so you form the same volume of gas at the end, no matter what the temperature is. You also, I think it's worth noting that there is a certain minimum that you must have, a certain minimum temperature, because if you have the temperature that's too low, although that's nice and cheap because you don't have to spend too much energy on energy resources, what happens is that you just end up with a whole bunch of unsuccessful collisions. Okay, and that's no good when you're working in industry. Okay, right. Finally, for this lesson, catalysts and rates. So here's a catalytic converter that's contained in the car. Basically, at the high temperatures that are in a car, you actually have hot enough conditions for the nitrogen and oxygen in the atmosphere to form what's called nitrogen oxides. So nitrogen harmless, oxygen we need for respiration, but at those temperatures inside a car engine, you actually find that you form nitrogen oxides, which can react with the atmospheric air to produce nitric acid, which is a part of acid rain. What you also find that there are some particulates in there, some hydrocarbons that have come from the fuels that haven't been burnt efficiently. You also got carbon monoxide because perhaps in that part of the car engine you haven't got enough oxygen reaching the fuel, so it's an inefficient engine. So all of those three gases plus these sooty particulates that you find, particularly with heavy fuels like diesel, have to be dealt with, and that's what a catalytic converter does. A catalyst is a substance that is added to a reaction to change the rate. So these will eventually break down, they will change, but it's not at a timescale that we want. We want it to be very, very quick. We want it to be happening before it's released into the environment, before they wreak their havoc. So what a catalytic converter does is it uses the catalysts, the chemical substances on the inside, which in this case is actually some precious metals, things like platinum and rhodium. We actually find that those metals break down these chemicals to form harmless products like nitrogen and water and carbon dioxide. Well, carbon dioxide is less harmful than the carbon monoxide coming over here. So, there is a little bit of compromise there. But the catalysts can actually do that at a much lower temperature. They can actually do their reactions with less energy, because a catalyst will lower the amount of energy required for the reaction to occur. What it actually does is it allows a surface for these gas molecules to sit, for them to do their reaction, and then the gas molecules move away. Because the gas products move away, the catalyst is not used up. So the catalyst isn't actually involved in the chemical reaction in such a way that it gets used up. So the catalytic converter can do its job constantly, day and night, as long as it remains clean and there's no dirt to obscure the surface of the catalyst to stop these reactants reaching the catalyst. The catalytic converter can last a very, very long time. So catalysts are substances that are added to a reaction to change the rate. They lower the amount of energy required for the reaction to occur, and this means that more of the collisions will be successful, because there's a barrier that you have to overcome between an unsuccessful collision and a successful collision. But if you make it easier for the chemicals to react, you don't actually have to have the particles bumping into each other at such a high pace. You can actually get a successful collision when you actually have lower speeds in your particles. The catalyst does not take part in the reaction directly. It does not get used up. It is very important to remember that when you're thinking about manufacturers, because catalytic converters are extremely expensive. Let's think about the questions. So, which essential piece of equipment is needed for all rate investigations? Pause the video. Well, what we actually have to do is we have to measure the time. So we are measuring the amount of product, we are measuring the amount of reactant, we think about that, but we also have to measure it over a fixed period of time. Okay, so an essential piece of equipment is a stopwatch. Second question, why would it be difficult to monitor the effect of temperature on an explosive reaction? Pause the video. It'll be very difficult because what you have to do is you actually have to see what the temperature increases are, and that could be quite a dangerous thing. In an explosive reaction, it's very, very easy for us to actually have our equipment measuring temperature differences actually be destroyed. Right, the graph in figure 5 showing a curved line of best fit, not a straight line. Pause the video. The reason why it's showing a curved line is because as time goes by, the reactants are gradually decreasing in concentration. So the rate of reaction is gradually decreasing as time goes by. It's not a sudden case. It's not like as if all of the reactants can react and it maintains its rate of reaction at the same rate. So you don't get the same amount of product or the same amount of reactant used up, same amount of product produced. You don't get that constantly until all of the product is made, and then suddenly the reaction rate is 0. If the reaction rate is 0, that means that you have a horizontal here. So the graph is not a straight line; it's a curved line at best fit. The reason why is because you have gradual changes in reaction rate, and you have gradual reactions rate, gradual changes in the reactants, I should say, and gradual changes in the reaction rates. Question number 4. Why does temperature have such a big effect on rate of reaction? Pause the video. Well, particles have more energy at higher temperatures, so when they collide, they'll be more likely to have enough energy to react, and that's a real combined effect. The stored kinetic energy of particles bumping together is a vital part, because particles must collide. So that's the reason why it's such an important effect. So much so that in some reactions the rate can be doubled by increase in the temperature by just 10 degrees. So the answer is that the reason why it's so important is because particles need to collide in order to participate, in order to take part in chemical reactions, to actually change reactants to products. But particles need to collide successfully. Not all particle collisions result in a chemical reaction. So the particles need to have enough energy to overcome the energy barriers to break bonds. Think of the example, finally, of an acid and carbonate reaction. Write a word equation, explain why the methods in figure 2 would be appropriate, describe how you would vary the temperature safely. So figure 2 is here. All right. So think about the first question. Write a word equation. So this would be acid and carbonate. Okay, pause the video. Well, it could be any metal carbonate. I'm going to choose calcium carbonate, and I'm going to choose hydrochloric acid because that's very commonly used. So we're talking about this reaction over here. We can have marble chips, calcium carbonate plus hydrochloric acid reacts to form carbon dioxide plus water plus calcium chloride. So that would be a word equation for it, but any suitable word equation would be fine. The next question, explain why the methods in figure 2 would be appropriate. Pause the video. Well, it's appropriate in several ways. First of all, the cotton wool stops the spray, so you actually contain the solution. Second thing is that the cotton wool allows the gas to escape, so it's very safe. The third thing is that this is actually a very safe method to use. All you need to do is just put it on a measuring scale, and so long as you have enough mass for the scale to pick up, the measuring balance to pick up changes in mass, it's very, very suitable. Over here, this is another suitable way. The reason why is because you actually don't have any of the gas escape, and you can actually control the volume, and you can read that constantly. You can read this constantly, but this is very, very visual as well. The advantage of a method like this is you can connect your measuring balance to a computer as well. So long as you don't have too much gas or more gas produced than you actually can contain in your gas syringe, then that's a very suitable method as well. Okay, right. So that's your whistle-stop tour of 10.3 temperature and catalyst. Do spend quite a bit of time on this video because I know that we spent most of our efforts on Seneca and studying it through Seneca. There is one more video which is going to talk about concentration and surface area, but you know, I hope you can watch that video. I hope you're revising in time, year 8. So stay safe, keep going. You've only got one more video to revise. Bye.